Now consider the DFT example. I would like to use this example, so I would like to recreate Excel. Number of sample at this moment I would like to use 128 point, and gating time is firstly I will try 2 seconds, and then sampling period will be P2 over P1. Okay, this one is a sampling period, and the sampling frequency is 1 over TS. Okay, and sampling frequency and the radian angle is 2 times pi times this one. So this one is radian per sec. This is unit for the omega s. At this moment, the number of sample is n, so the frequency step d omega is a 2 pi over number of point sample is this one. So this is a frequency domain frequency step, as we talk about in case of DTFT. The frequency step is 2 pi over n. This is this one is corresponding to this value. I would like to make index n, so this is 0 and plus 1. So number of sample is 128, so it is 128 point, and that is 128. I added 10 more, 138 will be the total number of point is 127. 0 to the 127 is 128. Number of point is 128. Okay, I create the bin index over here, and the time series can be given this product of time step. Okay, I make it constant. Then this one shows that the time step. Okay, I think this is time step, and I would like to create time sequence at here. The sequence at this moment I would like to create this red curve that can be created by summing of 3 spectral contents. One is the fundamental frequency, that is at this moment is 1 Hz. So 2 times pi times frequency is 1 Hz, and product of time B11, this is time, and plus, and the third harmonic component should be added. So sine 2 times pi times frequency is 3 at this moment, and B11 is time index. But I have to scale down 1 over 3. So this one is 1, this is 1 over 3, and 1 over 5th. So another one is a 5th harmonic component. That is a sine and 2 times pi times frequency is 5 Hz and B11. And that should be scaled down 5. So this is the red curve. So I'd like to make it flat. And then I added a plot. That is, I took data. At this moment, I plot this one, and the x-axis is 138, and data is also 138. Okay. I plotted 2 periods. 1 period and 2 period. That's this one. I plotted only 2 seconds. And the next one is to find out the frequency step. Frequency at this moment I would like to plot that one from 0 to the 2 pi in between here. So omega corresponding this area. The omega can be given, it's a quite similar TS. This is the n times and frequency step, as we have done in the time sequence. In time sequence, we producted. We make a product, the index times time step. But in the spectral domain, we product index times the frequency step, like that. The end of the frequency step is 2 pi. Okay, this one. So we would like to plot of the DFT of the signal. To do that, we talk about the frequency from index from 0 to the 1.5 is the Nyquist rate. So at this moment, we have 128. So this one is 0 to the 64. Half of the half of n is 64. That's the Nyquist frequency. So this is the Nyquist frequency at this moment. This position corresponds to this Nyquist frequency. Okay, this one is the half of the number of points. N is 128, so n over 2 is 64. That's the maximum frequency. This is pi. So in the frequency, index is 64, but the normalized frequency is pi. Okay. I would like to interpret this one. You know that omega is normalized frequency, but what is the actual frequency? Actual frequency is we have to make it frequency by dividing 2 pi. So because this is radian angle, and to denormalize this one, I have the product of frequency step, the sample frequency. So this one means the actual frequency. So think, okay, I have to make it constant. Okay, and then make it work. So this is a DC component, 1 Hz and 2 Hz. You know that we have signal 1 Hz and 3 Hz. So this one is 1 Hz signal, and this one is a 3 Hz signal, and 5 Hz signals. What is the Nyquist frequency? You know the 64 is the sampling frequency, then frequency 32 is the Nyquist frequency. Let's consider that one. This is the Nyquist frequency. Okay. Normalized frequency is it's a pi, but in the actual frequency is 32 Hz. Okay. You know that the half of the sample frequency. That's the actual frequency. This one is a normalized frequency, but this one is a radian angle. This one is a Hertz. Okay. And then I would like to find out the DFT of these signals. To find out the DFT, I would like to use Fourier transform. In the Excel, if you didn't find this Fourier transform menu, then you need to install that one into the additional function can be added from here. So you can add analysis tools that will provide the Fourier transform functions. So anyway, I would like to use a Fourier transform function from here, Fourier transform, and first I have to choose the Fourier transform range. So at this moment I would like to transform 138. That's the XS sequence positions, and the output will be stored from here 138 point. So this one is a Fourier transform. If you take the inverse Fourier transform, you need to select this one, but at this moment we need to take a Fourier transform, so make it work. Okay, this is the Fourier transform of this XS. Then I would like to find out the magnitude of that one, absolute value of xk. You know that this is the same as index k. So this is 0 to the any index. So k refer to this index and also refer to this index. Okay. I would like to find out the magnitude of this one. I am ABS, and then I can find out magnitude of that one. And I would like to plot the spectrum. I need to only plot up to here, but I can plot the whole range also. So first I would like to plot the whole range. Okay. So okay, here data is selected. This one I would like to plot the magnitude. X range at this moment I would like to use the normalized frequency. So 138. This is the normalized frequency. And output data is this one, 138. Okay. Then look at here that the pi is around here. Pi is around here. This one corresponds to this part. This one is this one. So you can see here that this part around the, the 2 pi is around here. So this part corresponds to this area. And this part equals to this part. So in the Nyquist frequency is around here. So we only need to plot up to pi. So I need to reduce that one up to here. So this is the Nyquist frequency. This one is 1 Hertz, and this is 2 Hertz, and this one is 3 Hertz and 5 Hertz. But this one is a normalized frequency. We cannot read out that frequency component, so I need to change the X variable. I can change the X variable. Editing, and I would like to change X variable. So X variable I would like to change up to here, 138 point. Okay, then X-axis now frequency, so I need to turn off. Okay, this is 0, and this one is maximum. I would like to plot up to 32 Hertz. That's the Nyquist frequency of this one. Okay. Then you can see that this is 1 Hertz. This is Nyquist frequency, but I can reduce that one into 6 Hertz. Okay, let's just look at here. Oh no, 6. 32. Okay, that's 6 Hertz. Then this is 1 Hertz and 3 Hertz and 5 Hertz. We can refer to that way. So this one corresponding to 1 Hertz and 3 Hertz and 5 Hertz. In the normalized angle is 1, and a normalized one is 0.049, and this one is 0.029. And this one is 0.49, like that. I'd like to change this one again to normalize the frequency. So this is better to express. So this is it. And I'd like to confine the data up to 3.14. That's the, okay, 3.14. Okay, this should be 0. Okay, then this is Nyquist frequency. This one is a fundamental frequency is 1 Hertz and 3 Hertz and 5 Hertz, like that. So we make the discrete time Fourier transform by use of this waveform. And what if I increase the gating time? If I increase the gate time, the sampling frequency will be lowered. For example, I taking the 4 seconds, then the frequency, maximum frequency is 32. We have a 4 period of the data, and I need to recalculate the Fourier transform. Okay, retransform. Then spectral contents will be changed. This is one. Actually, at this moment, the Nyquist frequency is 16 Hertz. In the previous, it was 32. Okay. If I plot this one to pi, then we can see like that. This is one is Nyquist frequency. This is a sampling frequency. So this part is a positive frequency part. But this one actually negative frequency part. As we talk about this one is positive frequency, but this one, that is the same as this one. This one, that is a negative frequency component. Okay. So I need to 3.14. Okay. Okay, I would like to check up that this gating time, at this moment we are measured up to 4 seconds. Even though we reduced the sampling frequency, we gated more longer times. This is the window size. We take this big size of rectangular window, but if we taking 2 seconds, then we only take this part. Okay, then we have only, you know, that this is 1 second and 2 seconds only. Then spectrum will be different, this part. So to check up that one, I need to take the Fourier transform again. So it looks like this way. If I increase this gating times up to 8, what happened? I measured it 1 second, 2 seconds, 3, 4, 5, 6, 7, 8 seconds. So I measured 8 seconds. Then sampling frequency will be 16. And what happened in the spectral domain? Spectral domain resolution is increased because of the larger window size. So that's this effect. So this one is a Nyquist frequency, but this frequency you can see, you get 1 Hz and 3 Hz and the 5th Hz. We can see more clearly. This one, the effect of the increasing the gating time. Okay. Another example by use of waveform tool. I would like to generate modulated signals. Okay, this providing FM and AM modulation. Let's check up AM first. I would like to scale source and the data change. You know, the carrier frequency is 1 kHz, but the data change is 100 Hz. And the modulation index, I would like to use 50. It means that this one is a half of them. You know, the blue one is a carrier frequency, original sinusoidal signal. But by modulating the AM signals, this part is increased 50%. But this part is reduced 50% of the original carrier signal. So original carrier amplitude is 1. But by using the 50%, if it is 0 cases, 1 over 0 is the data port. So 1 over 0 is modulated here. So 0 cases is reduced to 50%. So the amplitude is 0.5. But in case of 1, data is 1, then it is 1.5. 50% is larger. If I create this one and I apply this signal to the scope, and I measure that the waveform. Okay, I need to open the scope, and at this moment I running, then I can measure that the modulated data. So this is trigger point. If I increase that up to 10 Hz, it looks like this one. What about 5 MHz? So this is 101010 is transmitted by use of AM modulation. Okay, and this one measured that in the time domain. What if we can measure that in spectral domain? That can be done by taking the Fourier transform. That's this one. What is this one? So look at here that we have a 160 kHz sampling time. So I would like to reduce the sampling time by increasing gating time. At this moment, measured time period is of minus 50 to the 50 seconds. So I measured 100 milliseconds is gating time. And at this moment, sampling frequency is 80 kHz. Then Nyquist rate is 40 kHz. That's this one. I generated 1 kHz carrier one, and modulated one is 100 Hz. So I need to look around here. So I need to reduce the frequency like this way. So this is 1 kHz, and this one is 900, and this is 1.1K. So this one is baseband spectral contents. The frequency resolution around here is not that much clear. I mean that if I measure from 500 Hz, and the maximum frequency is about 1.5 kHz. Okay, 1.55. So that's the frequency step. So this is 1 kHz, and this is 0.9. This is 1.1K. and minimum value I would like to confine this up to 100 Hz. Okay, this is a spectrum of this the AM modulated signals. Okay, if I increase the number of gating time, at this moment I measure only 100 milliseconds, but if increasing that one up to 5 milliseconds, you can see the frequency resolution is greatly increased. Okay, and what about the windowing effect? I said that the windowing are shown here. At this moment I use the flat top window, but if I change to the Henning window, it has this kind of spectrum, and noise flow are shown here. And still it shows that the 1 kHz and 0.9 and 1.1 spectrum are clearly shown here. And if I using the Hamming window, it looks like this one. What about the Kaiser window? This is the Kaiser window. And if it didn't take any window, that is rectangular window. That's this one. The spectral shapes are changing depending on the window. I talk about that window effect over here. So I talk about the flat top window. That's the this is the flat top window. If I taking this window, the periodic boundary is converged to the 0. So if I taking Henning window or Hamming window, it looks like this one. So Henning window is almost 0. Hamming window, there is some still residual at the periodic boundary. So you can see here, this one is a Henning window. Henning window is this window. Apodization means that we make it continuous by making 0 at the left and the right edge of the data. But what if taking the Hamming window? Hamming window, there is some residual at the periodic boundary. In that case, spectral leakages, some spectral leakage exist here because of this the nonlinear discontinuity at this boundary. Okay, that's the this spectral leakage are increased. We can using the flat top, we can noise flow looks like this way. And if we reduce the gating time, so what's going to happen? The spectral resolution is poor. But if we increase number of sample, you know that number of gating time, the resolution bandwidth is increased. You need to think about the reason why the spectral resolution are depending on this time difference. What about FM modulation? We talk about the AM modulation out here. So I'd like to change that one into FM modulation. At this moment, the carrier frequency 1 kHz, and this one is 100 Hz. So that's the okay. I would like to change this one. 100 Hz means the data rate. So 1 0 are repeated with a 100 Hz rate. Okay. So modulation index, for example, if I taking 50, then frequency in one cases the 50% of the frequency of the 50% of the carrier frequency. Carrier frequency at this moment is 1 kHz. 50% modulation means 500 Hz are changed. So if I taking the 0, then that cases the red line frequency is 500 Hz. If I take in data is 1, then that is a 1.5 kHz. That frequency spectrum difference is very big one. So I'd like to change that one up to 10%. 10% means that if data is 1, then 10% of the carrier frequency, that is 100 Hz. So that is 1.1 kHz increased. If I taking 0, then 10% of this frequency are reduced. That is a 0.9 kHz. So look at here. The spectrum seems like it's similar. This is 1K, this is 0.9 and 1.1, because that is a 10% of the carrier frequency separation. You know that this one is a 10% carrier separation. And if I close look at in the time domain, if I look at in the time domain clearly, so I increase the time resolution, but the spectral resolution is very poor. Okay, but if I sacrifice time resolution, time resolution is poor, but the spectral resolution is fine. You need to understand that if I increase the gating time, the time resolution is poor, but the spectral resolution is increasing. But I'm increasing the to clearly see inside of the spectral in the time domain. If I increase in the time domain resolution, spectral domain resolution is so poor. So that is a trade-off. Okay? If I a little bit increasing, then spectral resolution is far better than previous one. The further increasing gating time is much better, but in the time resolution is poor in this case. So you need to understand the trade-off between the spectral resolution and the time resolutions.